Okay, so let's go. Hi everyone, Maxime here. So thanks for joining us today for NF Core bite-size talk focused on pipeline. This week it's Payam from the National Bioinformatics Infrastructure Sweden who is going to present us MetaboIGNITER. As usual, we're on Zoom and YouTube. If you have any questions, please ask them in the chat. Gisela and I will take care of them at the end. Over to you, Payam.
Thank you, Maxime, for the introduction. Let's get started with the presentation straight. We're going to talk about metabolomics, which we often define it as the measurement of small molecules. And these molecules, they're often between 50 to 1,500 daltons, and within this range, you will find sugars, lipids, amino acids, hormones, and so forth. And one of the important things about this metabolome or metabolomics is its closer link to the phenotype. And as a result of that, it has been used in various different areas, various different industries, including healthcare, of course, agriculture, food industry, and so forth. In this context, we can define untargeted metabolomics as a methodology to basically detect and measure as many as metabolites as possible in a given sample. There are various different instruments for doing that, various different methodology for doing that, and the one that we are targeting is called liquid chromatography mass spectrometry, or in short, LCMS. And this is basically a toy protocol that describing how it's been done. You start with some sort of sample metabolite extraction, either by liquid-liquid interaction or by precipitation of the proteins. The metabolites will run through a chromatography column, which is coupled to a mass spectrometer. They get ionized. The intended instrument, their mass to charge ratio will be measured, including their abundance. And then it will pass through the data analysis or the pre-processing. The different kind of signals that we get out of a mass spectrometer, it's called MS1 and MS2. MS1 data is normally used for the quantification, and that includes the retention time. That's the time that it takes for a metabolite to go through this column, and then it ends and enters mass spec. And I'll show it on the x-axis over here. We have the mass to charge ratio. That's basically the measure that is done by the mass detector inside the instrument, and I show it on the y-axis. And the measure signal is basically the relative abundance of the metabolites. I prefer to sort of show it as this as the intensity of the color, and we often call it the intensity or abundance. In different contexts, you might see this kind of plots. These are essentially the same thing. It's called an intensity map or even a heat map. If you zoom in, you can see the same pattern that I showed you in the previous plot. This one is essentially the distribution of the ions. Either people plotted over the time or over the mass range. But we are going to stick with this kind of simple representation. And one important point that I want to make here is that when we measure molecule, it comes in different signals, not a single signal, into mass spec. One of the signals that we get is called the illusion profile of the molecule. That's, as I said, for a single mass, for a single molecule, this is the time taken for a molecule to pass through the column. If you have a good high resolution instrument, we might be able also to find the isotopes of a single molecule. These are essentially the isotopes naturally happening in the nature, and often we see it with the 1 Dalton mass shift between the monoisotopic peak of the metabolite down here. Another pattern that we see is called adducts, and depending on matrix and what kind of sample laboratory procedure has been done, we might get different sort of element making the bond with our molecules, and that they often cause some sort of mass shift. So we also see this kind of pattern. It's important that this is still the same molecule. It's just the way that we have been preparing the samples, they affect the mass of the molecule. what I often say is that the mass spectrometry process is a world of clustering. We do a lot of clustering in order to sort of cluster the similar ions, the ions that we think that are coming from the same molecule together. In this case, we each box basically cluster the illusion profile of one metabolite, including its isotope pattern. You can also do the cross box clustering, and that's for the ad hoc detection. Each of these lines, each of these guys along the time, they're called mass traces. And when we draw a box around it, when we cluster the mass traces of different isotopes of the molecules, they are normally called the feature, so feature detection. This process is normally done per sample. So each individual sample is being processed here. But what we often have is basically multiple samples. So what we need to do is that we need to do another round of clustering in order for us to say that this metabolite is this metabolite in the sample too, right? So we basically want to link them across different samples. Now it comes with the problem of the chromatography shift. Time shift can be different between different metabolites across different samples, and we can also have the mass deviation. What's happening is that some sort of alignment is being done between different samples, basically map them to the same scale, and then we can do the clustering to find the corresponding metabolite. If we fail to do this kind of clustering, like this example, then we end up with having missing values. This is essentially a quick introduction on how this kind of quantification is performed, and at the end of this stage, we can essentially extract the MZ of the metabolite, the retention of the molecule. So we still don't know if they're metabolites or not. But what we have to do is that we have to identify them. I mean, one sort of naive approach can be to basically take this MZ of the metabolite, take it to any of the databases, and then search it with some sort of deviation boundary. And this turned out to be a very low accuracy. I mean, in this case, I just took one MZ and the search and I got 166. So one point I want to make is that this kind of identification is to a large extent problem of ranking. The way that we rank the metabolite, as the true metabolite gets higher rank, is the better, right? What we want to do is that we want to incorporate as much as orthogonal information as possible in order to improve this ranking, so our sort of true metabolite come the top of the list. One type of this orthogonal data that we use is called the MS2 data, or fragmentation, or tandem spectra. In this case, the mass spectrometer, now depending on the setup, will select a few ions and then break them apart. So the molecule will break apart into different pieces, and then these pieces will get measured again by mass spec. And what we're hoping is that we can do the same thing in the databases that are available out there, and then try to figure out whether what we have done in silico match what we have done in the real experiment. And there are different methods for doing that. The databases searches, de novo reconstruction, and the hybrid approach. But I guess the most common one is a hybrid approach that basically we wrap the data set into some form, in this case a tree, and then try to sort of score the trees together in some sort of model, and then try to infer the metabolite without going too much into the detail. Our workflow, MetaboIGNITER, tries to sort of automate these steps that I was talking about. What we provide is obviously the quantification, and we provide the parameter tuning. We provide two different quantification packages that user can choose and combine. 3+1 identification engines that I will go through. We provide QC and noise removal, and the whole thing can be done on pause and neg, both combined or in solo. For the quantification part, we start getting the raw data or the MZML files converted from the user. We do an optional centroiding or peak picking. We have an optional parameter tuning, automatically tuning rest of the parameters over here, and the parameters from here will be propagated throughout the workflow. And this option can be done on a single sample, on a collection of samples, for example, if you have QC samples or something, or on the whole cohort. That will be followed by the feature detection or mass trace detection, either by XCMS or OpenMS, and then with retention time correction and grouping. The result of this will pass through a noise removal step, and that includes the blank filtering that basically filters out the signal which is present in the blank with the same magnitude as the sample. We have the QC filtering that removes or filters out the signal that is not stable over repeated samples. And finally, the dilution filtering, which filters out the signal which is not following a dilution series if you have done so in your experiment. And that will be passed through our sort of famous camera ad hoc detection and isotope detection, which the different features will be linked together across the time, and the isotopes will be detected ad hocs. And at this stage, if the user has selected not to do the MS2 part, the workflow is finished, we do some sort of transformation and normalization depending on the user choice, and then we provide tabular output. However, if the user has selected to do the identification, we keep the result of feature detection from the quantification part, we fetch it here, we read the MS2 data, we do an optional centroid of the MS2 data, and we do a mapping. This mapping is done in a way that we try to figure out the mass traces corresponding MS2 spectra to the mass traces. So essentially, we are mapping the MS2 data on top of the MS1 data in order for us to be able to say, hey, these fragment ions, they are originated from this specific feature. And this will allow us to sort of do some sort of MS1 driven clustering. And then we do what's so-called, we call it a hyper MS2 construction. And that hyper MS2 construction will put together, we aggregate all the MS2 spectra that are coming from, we think that they are coming from a single ion. Then various different pre-processing can be performed on this hyper MS2, including clustering, smoothing, or centroiding, and this can also be skipped. But we are hoping that by doing that, we reduce the number of searches required to do, and we also sort of capture different aspects of the fragmentation. At this stage, we fetch the ad hoc information again from the quantification part of the workflow. And then we feed this information together with MS2 to our mass calculator, and that will estimate the neutral mass of the metabolite, and we'll send them to different search engines. Now, Metafrag, CSI, Finger ID, and CFMID are supported, and they can be combined, or solo can be run, and that will be followed by the posterior error probability estimation for bringing the scores on the same scale and the tabular output. Another type of identification that we support, we call it the library identification or in-house library identification. This type of identification, if you think, the different labs, they might have different sort of purified metabolites. And the idea is that we want to say whether this metabolite is present in our sort of actual biological sample or not. What's happening is that we are willing to extract experimental MZ. We know the theoretical mass of them. We want to extract the retention time based on the chromatography setup that we have, and we want to find the MS2s for this compound. What we do is that we separate, or what's happening in the laboratory procedure, these metabolites will be split into different buffers in a way that in each buffer, we don't have metabolites with overlapping masses. And the idea is that we can later go and find these metabolites and find the retention time and the mass and the MS2. And it comes with the benefit of having, for example, the tailored or a very fine-tuned fragmentation pattern, or we can also use the retention time for matching to the actual biological sample. MetaboIGNITER can do both characterization and searching of an internal library. What we do here now, I'm talking about only the library samples, not the quantification sample. We get the library file, we do an optional centroiding, we do a feature detection exactly like we did for the real biological samples. The same thing for the MS2 data. We have an optional map, we have a mapping step that's not optional. At this stage, we get a list of theoretical masses from the from the user and the list of samples which the user know what metabolites are in there, and we try to sort of estimate the retention boundary of each of the metabolites, each of the sample, and then map it to the information that user has. That follows with sort of previously said the hyperspectrum. And at this stage, we fish the result of quantification and the identification of, and then we have an internal search engine that tries to sort of match the retention time plus the MS2 data and the MS1 data and try to find whether these metabolites are present in the sample or not. And that will be followed by the posterior probability estimation and the actual output. And that's essentially pretty much what the MetaboIGNITER does under the hood. Obviously, I mean, there's about 500 parameters that needs to be set. So I don't want to show the whole command, obviously, but we want to sort of guide you that okay, use the NF core interface for running the pipeline, and that gives you this sort of nice change to a file that you can basically input and run it. The inputs we are getting, the main inputs, they are the XML file, like obviously, and you need this sort of path referring to the XML files in the positive mode, negative mode, or any of the isolation. We accept the phenotype file. That's essentially a CSV file or a table describing what kind of MS1 data you're inputting into the workflow. And that pretty much in this, you have to put the name of the files and the class of the samples. You might have the biological samples, and you have this sort of the blank samples, dilution series, QCs, and so forth. You can define various different things. If you want to remove if you want to rename the samples later in the output, you can mention it there. If you have technical replicates, we can do averaging of them at a later stage. You can put any sort of covariates that you want us later to sort of link it to our output. We provide 3 different outputs, and all of them are tabular. We have a peak matrix, that's essentially the abundance matrix, that the variables are on the row and the columns are on the samples on the column. And though this is the raw data, but we can do a transformation also. The missing values are shown by the NA or non-assigned. The metadata file, which is essentially what you have been outputting, the user has been outputting into the inputting into the workflow, but we just reformat it and reorder it to match the peak matrix. And the valuable information is probably the most important output of the workflow, and that includes all the information that we have been extracting from each of the features in the data. And that includes, for example, the monocytopic mass, the different sort of IDs for the metabolites, the name of them, if we have been able to identify them, if they have been associated with any MS2, we also have MS2, and so forth. And this is only a fraction of the thing that I have been cutting here. So many different types of information is providing. At this stage, we are not doing the downstream analysis, and for a reason that we think that should be sort of done by the biostatisticians. However, the outputs that we are providing, they are fully compatible with almost all the tools that are in workflow for metabolomics that have been developing by workflow for metabolomics community, and that includes various different statistical tools, sort of normal PCA, PLS, network analysis, clustering, and so forth. So you should be able to sort of use this output basically out of the box with minimum modification. There are things on the table that we have been developing and soon will be part of the workflow. And that, I mean, right now we are only supporting MZML, but the conversion to the conversion from the sort of raw format is part of it. We are supporting 4 search engines, and the idea is that we want to sort of give you an aggregated result of the search engines. Right now, we are giving you 4 results, but the idea is that we do a sort of consensus ranking of this ID. We know that recently people came up with fantastic identification post-processing for metabolomics identification, mainly for the CSI finger ID, and that's going to be part of this. We are supporting right now, I think, 2 different alignment and retention time correction and grouping methods, but we are going to add more into it. Metabolite class detection is already part of the workflow. The parameter is not exposed to the user, but it will be, and it will be part of the output. And we are in the process of migrating to DSL2. It should not affect the user experience that much, but from the developer part, it's a big deal. I think with this, I want to thank all the people. I don't name people, but a lot of great persons have been part of this workflow in the past, I think 7 years or something. So I thank them all. This workload started as sort of a spin-off from phenomenal infrastructure, but they're supported by Elixir and the National Bioinformatics Infrastructure Sweden. And a big thank also to NF Core community. These guys are absolutely amazing, just help without any expectation. So thank you very much for listening.
Thanks, Payam, for such a great presentation. That was amazing. Yes, so I'd like to thank the Chan Zuckerberg Initiative for giving us the opportunity to do this series. And now let's hear if anyone has any question. So I don't see any question in the chat at the moment. Let me just check if we have any on YouTube as well. I don't see any question over there either. So it must have been like a super clear presentation. And I wasn't very like familiar with this field before, but I felt like I understood like most of it. So for me, it was like pretty clear, at least.
But that's great. I mean, if there was any question, I mean, I know that the sort of amount of information is coming is probably a big deal. But if there was any question, we are always ready in the.
Yes, otherwise people know that they can still ask you any question on the either the MetabolGNITER Slack channel or on the bytesize channel. Okay, then I think we're good.